Can I start? Hello?
Yes, sir, start.
Okay, so we will continue our discussion and we will work towards estimation of F2 and that's it. Okay. So okay, so stream consists of E1, E2, dot 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 EM in 1 to n, and we of course we know n in advance, and as you know, Fi is the frequency of I in the stream. And what are we supposed to output? So estimating F2 means I'm supposed to output this, right? So this is our question which we were trying to address yesterday. And already what we have seen for this is that using AMS, right? Using AMS, we can achieve this in sublinear space or a root n log n space with probability 2/3, right? This is what from yesterday it will imply. It was n to the power 1 minus 1 by k, right? N to the power 1 minus 1 by k log n plus log m, I think, right? So this is what it will imply. Okay, fine. Okay, but towards the end, we also started to see a better estimate for F2, and when I say better estimate in terms of space. Okay, so now our whole objective or goal is to get to polylog space. Okay, whole objective is to get to polylog space. Okay, and I want to achieve this with probability 2/3. And if you want to get accuracy delta, there will be also a factor log 1 over delta sitting here. Okay. So if you recall correctly yesterday, what did we do? And we came up with, we said that okay, for now let y1, y2 dot 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 yn be uniformly be a random variable, be a +1 -1 random variable, okay, that are, say for now, that are y is independent. Okay, we'll fix how much independence do we need actually when we do our computation. And then we said, hey, if this is what it is, then we said that, well, then the following object is a very good estimator. So we said z equal to summation yi fi, right? Fi yi is a good estimator in the following sense. We will output z square. Okay. Now we need to compute. What do you mean by it's a good estimator? We have to say the proof that expectation of z square is exactly what we want to compute, right? So we have to show that expectation of z square is equal to f2, right? And towards that, what we said, well, what is an expectation of yi? Expectation of yi is 0 because it takes +1 with probability half and it takes -1 with probability half. So half minus half is 0. Okay, and then what we said, what is variance of yi then is expectation of yi square, because minus expectation of yi the whole square, that will get cancelled because expectation of yi is equal to 0. Now, so this is what variance of, but what is the variance of yi? What is expectation of yi square? It is going to take, now what is the possible values yi square can take? Just 1, and it will take 1 with probability 1. right? So expectation of yi square is 1. So variance of yi is 1. Now if this question mark is at least 2 wise independent, if question mark is at least 2 wise independent, then what can we say about expectation of ya times yj is expectation of yi times expectation of yj, which is equal to 0. Okay, so this is what we saw last time, and which implies that what is z square? Z square is nothing but summation I fi yi whole square, right? This is what z square is. So if we write down this, what will we get? So I'm just writing this z square as a random variable. Then we are going to get summation over I fi yi whole square plus 2 times I not equal to j fi fj yi yj. This is what we are going to get, right? This is just formula of a plus b plus c plus blah 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 whole square. This is exactly what you will get. Now let's see what all things we can get rid of from here. So now look at this quantity, right? So now if I compute expectation of z square, right, I can apply linearity of expectation and get over all of these things. Now if I apply linearity of expectation to any term here, what I'm going to get is like fi fj expectation of yi yj, but we just now showed that expectation of yi yj is 0 if I not equal to 0. So if I take expectation of z square, this term will vanish, right? So what we'll get is expectation of z square is summation over I expectation of fi yi whole square, which is equal to what? Summation over I fi square expectation of yi square, but expectation of yi square is equal to 1, right? So this is equal to summation fi square. Okay. Okay. And then we proposed the following algorithm last time, okay, based on that, and we said, hey, we will try to compute other things today. So this is an algorithm which we proposed last time. Okay, so what was the algorithm? So okay, AMS 2S F2 estimates, let's call it F2 estimate. F2 estimate. So what I'm going to do, let y1, y2 dot 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 yn be plus 1 minus 1 random variable that are question wise independent, where question is at least 2, right? Because this is what we have already used. And now I said z is 0 while stream is not empty. Stream is not empty. What I want to do? I want to do, suppose Ej is the current item. Then I said, let's do z equal to z plus y Ej, okay? And while output z square, okay? So this is what, but a lot of, at least some of you had there were 2 questions which were asked to me. How do someone comes up with such kind of z, A, and B, why is this correct, right? Why is this object is same as this object, okay? So of course I don't expect you to give an answer because you have been told an answer. But do you realize why this output is same as this output? Do you get my question? Look, I'm going to output this z square, which I'm incrementing every time. Why is that equal to the random variable z, right? So my question is very simple. Look, even y z is equal to little z. So suppose I had my stream, suppose this is my stream, and let me run this algorithm. What will be adding? Let's write it down. Okay. So for 1, I will add what? Y1, then Y1, then Y2, is it same as what that Z is? How many times will this sum be updated by Y1? As many as the frequency of Y1. How many times it will be updated with Y2? As many as frequency of Y2, and that's it. Okay. So these two objects are same. Okay. All good? Okay. So this is why it is fine that we do it this way. Okay. So we'll get to this. Okay. Now, so now let's talk about the quality of this estimation. So to compute its quality, I need to compute its variance, right? To compute its quality, I need to compute its.
So when we are updating yi in that, is it? I mean, suppose y1 is decided. Is it the same yi or every time it is chosen at random?
No, it is fixed. Here I have fixed this, right? Let y1, y2, yn be this positive. Like I have already fixed them and then I did it. Okay. I mean, there are issues with this also, but we'll fix that in a minute. But this is what we did here. So I just wanted to put that into an algorithm. This is not a very efficient way of doing something, but we'll get to that. Okay. So what are we interested in now? We are interested in variance of Z square, right? If I want to apply Chebyshov, then I need to know variance of Z square. So how will the shape and size of variance of Z square will look like? Do you know how the formula of the power 4 looks like? I mean, 2 to was okay, but what about 4, 3? Okay. So what is Z square? Z square is the square of this, right? So now we are interested in Z power, like variance of Z square. So what are we interested in is expectation of Z4, right? This is what we are interested in. So what is expectation of Z4 is nothing but expectation. Let me write it down. Okay, so let's write it down. What is Z4, and then we'll try to write it down its expectations. Okay, so what is Z4 is summation fi yi to the power 4, which is nothing but summation I in 1 to n, summation j in 1 to n, I, j, k, l, okay, something, k in 1 to n, l in 1 to n, and then what we are going to get? We are going to get fi, fj, fk, fl, and yi, yj, yk, yl. This is what you are going to get. Okay. Now tell me which of this term will survive. If look at this, if I am taking an expectation, of a term here, where suppose my question is say at least 4, okay, so that now I can just break them out directly. Okay. Now, what happens if one of these terms appears exactly once? Then that term should vanish because expectation of yi is equal to 0. So no term where exactly one of these guy is there will there. So only term which will survive here where all the 4 are same or 2 2, right? Other terms will not survive. Okay. So what will be expectation of Z4 is equal to, and what else do you know? And for all other terms this is going to be 1, right? Because there are 2 terms of the same thing, so this is 1. So 1 1, if it is 4 thing, still you're going to get 1, right? So expectation of Z4 is summation I in 1 to n, right? Fi to the power 4, this is one term, plus some coefficient we have to choose, summation I equal to 1 to n, j equal to I plus 1 to the n, okay, because it is same as saying that I and j is not equal, okay, I just wanted to, and what it will be, fi square, fj square, this is exactly, and the coefficient which you will get here is like 6, some 4 choose 2 or something, so it's like 6, it's like 4 choose 2, right? So that many times the same term will appear, so it is like 4 choose 2, which is 6, right? So this is fine, so this is exactly what it is. Okay, so this is what expectation of Z4 is. Okay. Okay. So now I know that question mark is at least 4, right? But that should be enough for us. Okay. So I will say 4 wise independence. This is why we needed 4 wise independence, no other reason, right? For our computation, we want to like be nice. Okay. But now what I am interested is computing variance of Z square. And what is variance of Z square? Variance of Z square is expectation of Z square minus expectation of Z whole square. Did I write something wrong? 4, and this should be 4, no? Expectation of Z square whole square, sorry. Okay. Okay. So what is expectation of Z4 is this term which we just computed. So summation I in 1 to n fi to the power 4 plus 6 times I equal to 1 to n j equal to I plus 1 to n fi square fj square, and then minus of what is expectation of Z square. We computed this quantity here, no? Summation fi square. So it is just going to be this is going to be f2 whole square, okay? But what is this term? Is just f4, right? So what are we going to get? We are going to get f4 f2 whole square, okay, and this term plus 6 times I equal to 1 to n j equal to I plus 1 to n fi square fj square. This is what we are going to get, okay? Okay. Okay, what is f2 square? We'll get, if you look at f2 square, we'll get whole f4 and twice this term, right? So this is why I can replace this with f4 minus another f4, because I'm just taking that sum and doing this, and I will get plus 2 times summation I equal to 1 to n summation j equal to I plus 1 to n, right, fi square fj square. Okay. So now what all things will get cancelled? This and this will get cancelled, and 6 minus 2 is 4. So what will we get here is 4 times summation I equal to 1 to n summation j equal to I plus 1 to n fi square fj square. Okay. And what is this? This is definitely less than equal to 2f2 square. Right? Right? So this is what we have been managed to show. Okay, great. So how will we? So what is a? So what is a? Now let's try to apply J which up. I don't know. That's why I carry this book all the time. Okay. So this is what it is, right? Probability that x minus expectation of x is greater than equal to some constant a is less than equal to variance of x divided by a square. Okay. So in suppose, as I told you, right, suppose we fix a equal to some epsilon times expectation of x in our setting. So what will be this? Probability that z or z square, what we had? We had z, right? Right? So z square minus expectation of z square is greater than equal to, say, some epsilon times expectation of z square. And what is expectation of z square? Is f2. Okay. So let's write it down. f2 is less than equal to, okay, what is variance of x? 2 times f2 whole square divided by, which is epsilon times f2, yeah, which will mean 2 over epsilon, right? What? By epsilon square, sorry, right? So what does this means? So if we take an average over some order 1 over epsilon square estimator and return you the average, right? Right. So I independently do not one such object, but I independently carry out this algorithm AMS F2 estimate for z square. So like I do z1 square, z2 square, dot dot dot, say z 8 over some epsilon square, right? Right? And then your z tilde is, or say p, so and z tilde is like summation zi square divided by p. If I return that, then we know that I can control, and if I choose p to be roughly order 1 over epsilon square, then I can make this error bound to be constant, right? Do you get my point? Suppose I wanted this to be less than or equal to, say, some fixed constant 1/4, right? If I wanted this to be less than or equal to 1/4, you choose your constant, fixed constant, say 1/4, then it will tell you, right, that okay, then you have to choose 2 by epsilon square has to be less than or equal to 1/4. Then if I repeat these many times, then that guy will add up here, so that will cancel out each other. So you just need to repeat that many times. Okay, excellent. So what did we learn from here? We learned that, and look, if you wanted this to be less than or equal to delta, then you can do the trick of applying this with constant and then grouping this and do all those kind of things. But if I'm happy with a constant success probability, then all I have to do is order 1/epsilon square times this. Okay. Okay. So that is, so this is, so after this there is not much happening. You just, once you compute your variance, you accordingly choose number of times you need to do this to take this average, so that you achieve this with constant success probability. And if you want to achieve this with probability like at least 1/delta, then you group this and do the median trick. Okay. So basically, if I wanted this success probability, if I wanted probability, uh, z square minus expectation of z square to be greater than equal to epsilon times f2 is to be less than equal to delta, if this is what my objective was, then I can achieve this in how many rounds of this algorithm, how many independent rounds of this algorithm or trials of this algorithm is 1/epsilon square log 1/delta times whatever space this algorithm takes. Now let's go back to this algorithm and let's try to analyze the space. Okay, what does it mean that I choose y1 to yn be a random variable that are 4 wise independent? It was okay because that is how we set up our experiment, but this is not how you can, because then if you are going to depend, like you are going to pick up these y1 to yn, it is going to take you n bits. So I cannot have n random variables sitting here independently. So somehow I have to fold them up, and this is why what we do is not this, but we let h be a random variable, right, from n to -1 to 1, okay, be chosen from a 4 wise independent hash functions h. That's it. Okay, and then everything is fine. And to do this, we know. So now so we can achieve this. We can store a k log n, k wise independent random variable in order k log n bits, right? So for 4 log n bits, we need how much? 4 wise order log n bits, okay, plus to store z, right? How much it will take to store z? Huh? And now the algorithm will change, by the way. This is not y is a, it will be h of ej. Log, okay. So in the setting which we work, like, yeah, so bits, okay. So this is going to take us epsilon square log 1/delta log n plus log n bits of space. Okay, question. Question? Okay, so let's zoom into this algorithm a little bit more and try to get more out of this than what we have managed to do this. Okay. Suppose would have mattered if I wanted F2 estimate for some number F1, F2, dot dot dot, Fn, some number F1 to Fn, okay, where these numbers could be negative. Do you understand my point? Look, up until now, I said you that my numbers are coming from 1 to n, and we are just updating things. So fine, and I want it. So forget about what does it mean. Like, let's not get into the question of like what does I just want to compute this quantity. So like, I don't know. You are going to give me some number from say natural numbers. Okay, you are going to give me some things from the natural numbers for now, natural numbers, right? And as I told you, right, so suppose these natural numbers, and I all know that there are n bits n position, okay, and I was talking about this before, and at ith position I will tell you to increment by some number, okay, +2, -2, anything I can tell you, not natural numbers, sorry, z, okay. So how it is going to come? I comma delta, where delta is the element of z, right? And now I am still interested in computing summation fi square, where fi is the number at ith coordinate. Now my question is, so suppose this is my new definition of f2, does my estimator still work? Do you get my question? Right? Now suppose I have this positions, okay? So let's write it down. I will leave this. I will leave all this. Okay? Unfortunately, this board is too small. So what is this? What is the model now we are going to work with? So this is exactly what I was trying to tell you, that now suppose x is 0 to 0, some n bits or n positions, okay? You start with this n position, and every stream element is of the form I comma delta, which means that look at the ith bit, okay? So what is xi? After that you make it xi plus delta. So you update it. So now the updation can be plus, updation can be negative, and what are we interested in and what I'm going to call f2 now, or f2, I'm interested in computing xi square. Okay, this is what I'm interested in. And now my question is, whatever algorithm I just taught you, would this also work in this model? Because now notice there could be negative updates. There could be not only positive updates, there could be negative updates. Right? And I can also ask more fundamental question, that why I delta in z, why not delta in r? Of course, there's a precision issues, but forget about those things. Why is our estimator doesn't work or work? Okay, so let's just do our computation of estimator. Our estimator was, so what should be my estimator now? What is my estimator?
We have never used the fact that the frequencies were negative in this direction. We have never used or negate the fact that the frequencies were positive or negative.
I don't know. So this is what I mean. Actually, the way it is. For the reason why I wrote like this is that I just wrote like this because for 2 it doesn't matter, but for all other quantity it matters whether it is negative or positive. So basically people take absolute value and take square. That's like a norm estimation. But for 2 it doesn't matter, so I don't want to get into that for now. Okay. Okay. So you know that what kind of, and say delta is in R. Now how do I compute this? So what should be my estimator? What should be my unbiased estimator? What should be my unbiased estimator? Before, all of you said that, oh, take z equal to summation fi yi. This is what exactly what, where it was fi yi. So what should be the corresponding term here? What happens if I doubt? No. Xi, yi. So suppose at the end of the stream, what I have left is x1, x2, xn. Okay? And for each of these guys, I have this random variable y1, y2, yn. This is my random variable. Okay? Which are whatever y's independence we need, we will make them. Suppose this is what, so what is my expect, and I will still return z square. So what is my expectation of z square? Right? And yi's still take values between +1 and -1 with equal probability. So what will be this expectation of z square? Right? It is exactly the same thing as before, because if yi yj I not equal to 0, j, it is going to be 0. If I is equal to j, it is going to be 1. So this is going to be summation xi square. So estimator works perfectly fine. There was nothing wrong with my estimator, right? Huh?
That step can't work, right?
I understand that will not work. We have to change accordingly. What step will not work? Yes, I know this is not going to work. So what else will work? Yeah, I know this will not work. It's just that one has to make an appropriate modification. Okay? But if I would have been doing a variance calculation for this, what would have changed? Would anything change at all? Nothing. I mean, what I did at all, oh, if these are 4 y's independent random variable, if one of them, because you still have the property that expectation of yi is 0, expectation of yi square is 1, and if you start with a 4 y's independent random variables, then all but 1 also, if it is there, then it is going to become 0. So whatever your quantity here, fi, fj, whatever you see here, it will be replaced by xi square, xz square, and this will be, let's just, for want of better, let's call this is also called, this quantity is not called, this is called norm. Okay, norm. Okay, so now what will be, we will be able to bound this with this, and that's it, right? Nothing will change, and absolutely nothing would change here. Okay, but there are some things which will change, as he was saying. Now your stream is getting an ith element with a delta, right? So ej is the current item, is not. So what is the current item? Suppose I comma delta. So what should I do here? H is a times delta, that's it. It's like a weighted sum. Okay, so before I go further and get into show you some more properties of this, let's zoom back and let's look at this model a little bit more and tell what does it mean to have. Okay, so let's look at this model. Okay, so we can do an F2 estimate even in when you have a negative things and real numbers and everything. If this is a like we can do a norm X2 estimate in same amount of space as we did before. Okay, fine. Like all these calculations we'll just go through. Okay, but we will look back at this in a different manner in a minute. So I will, but I don't need this maths anymore. Okay, so you understood the model here, right? That you start with a vector x which is 0. So basically at the end you will get a vector x in Rn, but you start with vector x equal to 0 and each element of the stream is tuple I comma some delta and you update xi with xi plus delta. Okay, so this was one function which we wanted to compute about this vector x, but there could be different function that you would like to compute. Okay, okay, so first if delta j is greater than or equal to 0 or if let's call it j delta j delta j, I don't know why I am doing this, but fine. Okay, for all j, then this is called the model, this model is called cache register model. Okay, the reason I am just introducing it so that at least when you see this terminology somewhere, I mean you don't get hyped up what this is. And the special case is when delta j is 1. So like every update just increments everything by plus 1. Okay, if delta j is arbitrary, it is, this is exactly what is called turnstile model. Okay, okay, there's another model, delta j is arbitrary, delta j could be arbitrary, but x is greater than or equal to 0 all the time, right? So look, I started with all 0 vector. So you could do negative, but you have to still maintain that every coordinate is positive throughout the process. Okay, then this is called strict turnstile model, and this is called strict turnstile model. Okay, and there's a last model which is called, okay, it's called sliding window. W. So what is sliding window model? Okay, sliding window model. Interested only in last W items, and this is what is called window. So what last W items you have, like you, in your stream, you only worry about those, right? So then that is what is called sliding window. So like, okay, so these are the different models which you can make on this model. Okay, so basically, and the what is an objective? Objective here is always objective is to compute some function f of x, the vector x. Okay, so now I will go back to my F2 estimate. So what did we give? We did our F2 estimates in turnstile model. Okay, so we did our estimate in turnstile model. And for all other greater than equal to 2, if you look at what we were doing last time was this. This is CAS register model for whatever p greater than equal to 2, or p greater than strictly greater than 1. What we did yesterday was CAS register model, because you can always increase by plus 1. Okay. Now, so this F2 estimate is amazingly simple. Okay. Now let's try to understand some properties of this F2 estimate. So suppose you had sigma 1 is some set of stream, and sigma 2 is another set of streams, okay? And algorithm has computed Z1 here, and algorithm has computed Z2 here, okay? So what will algorithm compute? So all these things comes first, sigma 1, and then sigma 2 comes. What will it compute? Do you get my question? So when I ran this particular algorithm on stream sigma 1, it computed Z1. When I ran stream sigma 2, it computes Z2. Now I'm running a stream sigma, which is first sigma 1, then followed by sigma 2. So it's a concatenation of sigma 1 times sigma 2. What will it output? Huh? Z1 plus Z2. Excellent. Okay? Okay. Look, output of the algorithm is not this Z1 or Z2. Output of the algorithm is some complicated function of Z1, Z2, like it's square, right? So there is some sort of linearity happening here. So let me define the notion of sketch formally. Okay. So what is a sketch? So a sketch of a stream sigma is basically a data structure. It's a summary data structure. Zero, okay, ideally of small space, okay. Such that the composition of two sketches, okay, such that the composition such that the sketch of the composition of sigma 1 dot sigma 2, okay, of two streams is what? Sigma 2 can be computed from C sigma 1 and C sigma 2, okay. Output of the algorithm is a sketch. Output of the algorithm is sketch, is function of the sketch. Function of the sketch. Okay. So it's a very simple demand, right? That if I give you a sketch of two things, okay, and a sketch is linear, if, what is the property? A sketch is linear sigma 1 dot sigma 2 . So, question, what is the summary of algorithm for F2 here? Or what is the summary of the algorithm for F2 estimate here? Z. Is it a sketch? It is a sketch, right? Now, is it a linear sketch? Oh, what did I write? Not. Sorry. Is it linear sketch? Okay. So, actually this is a sketch and this is a linear sketch. And a sketch has found many usefulness in lots and lots of applications, lots of properties. And we will see much more starting from now on application of this. But notice, to get a constant success probability, what we did? We took in parallel order 1 over epsilon square run of this algorithm, and then we did compute its estimate. Okay. Now we can think of all this together as a linear sketch. Okay. So how? Okay. So let me write down a sketch version of this algorithm. Okay, and then we'll move to doing something else. Okay. So whether you do a sketch or you do non-sketch, it absolutely doesn't matter. Basically, even in so generally, how does a linear sketch works? Generally, it is a matrix. It is a matrix which is thin and broad. Okay. So where each of the row should act as an unbiased estimator of the object you have in it. Each of these row, right? So you are like, you have not gotten rid of coming up with an unbiased estimator trick. No, you have to, but you can just compute one estimator and just take several copies of it, right? So for example, for us, I'm going to fix L equal to, say, some C log 1 over delta C log 1 over delta 1 over epsilon square. Okay? This is what my L is. And what is M? What will be M? Is a, as I told you, right? It is an L cross N matrix. Why? Because if you recall, what was our estimator? Our estimator was, if you recall correctly, it was Z was summation yi times xi. This is what estimator I was trying to use. Now, all I want to represent is yi as this matrix, right? So I could have also written this as a dot product. If I had written y as a vector, I could have written this y dot x, right? If I think of y as a vector, y1, y2, yn, and x as x1, xn, then it is just nothing but dot product, right? So now what I do is that, okay, so I just take inspiration from here and I make my matrix. M is L times n because I need n columns. Rows are small, right? Because each row is an unbiased estimator, and we were doing averaging over 1 over epsilon square estimator. So this is why M is L times n, because L is fixed. So see, L is thin, but n could be very big. Okay? Matrix. And where should the entry be? entries will be from man plus 1 minus 1. If I'm telling you each of them is a estimator minus 1 plus 1 such that what is the property? First, okay, rows are independent. Secondly, okay, in each row entries are 4-wise independent, right? And what is Z? Is a L cross 1 vector initialized to 0. Okay. So while stream is not empty, what should we be doing? Okay. While stream is not empty, and suppose we get some aj equal to I comma some ij delta j, okay, is a current update. So how do I update my Z? Z is a L length matrix, right? Sorry, vector. So Z is nothing but m times, or rather delta j times m e what? Ij. And what is Eij? Is a unit vector. No, sorry, what is that called? Indicator vector, or okay. It has 1 at ijth bit, 0 everywhere else. I think it has a name. What is it called? Indicator vector or something. Unit vector, I don't know. Okay. So why it is fine? Because notice, this is L cross n, okay, and delta j is some quantity which will be multiplied with everything, and this is what will be the size of this Eij is also going to be n cross 1. N cross 1, okay. And while output Z as a sketch. Okay. So many things, okay. If we are going to store M at some L cross n matrix, then we are dead. Like then we will achieve nothing. What? It's not the copies. I mean, I wrote you what I wanted from, what properties do I want from my, right? Now look at each row, it is an estimator. Each row is estimator. You look at any set of rows, they are pairwise independent. How I am going to construct such a matrix? Compactly, right? Otherwise it is going to take a lot of space for me. What? L copies of? L copies of H. Is that enough? Can I take L copies of H and be good enough?
Pick L in, choose L at random.
L at random meaning? You choose H1, H2, HL, each HI from H randomly. They are different things than meaning.
I mean, just pick L many at random from the set of.
So how will you choose HI to HL at random?
From the.
Yeah, so I'm asking you more compactly how I'm going to do that job. If I need to understand how much space it is going to take, I need to know for H1 what should I remember, for H2 what should I remember, for HL what should I remember.
It may compute in space for logging.
Hmm?
For logging.
So, but yes, I understand that, but what will you remember? You get my question, right? I mean, I should explicitly know that these are the things which I'm storing for H1, these are the things which I'm storing for H2, these are the things which I'm storing for H3, so that I can compute things.
We store the 4 variables which are needed for each hash.
Exactly. So, when we chose this prime, we chose A0, A1, A2, A3 uniform random for first H1. Then I again pick up A0, A1, A2, A3 for this, keep that separately. For A2 again I go and pick up these 4 objects and keep this. So this is how you pick H1 to HL uniformly at random. Now each of them is going to take 4 log n bits because there are 4 numbers. So it is excellent. So this is how M will be represented for us, right? And of course I will have L, Z, right? Which is also going to take some L times, say some log n bits, okay? But what about update? Right? Something has come, now I need to update my Z. How will I update this? So for updation, what all things do I need? Z I have, but so think of this Z, right? Currently Z is Z1, Z2 dot Z L, okay? Now next it is going to become Z1 prime, Z2 prime, ZL prime. How will I do, given that I have all these things, how will I update this quickly? Delta J we have. So what is Zi prime? Into look, notice here, right? Except one entry here, everything is 0. And I can probably generate this entry completely by looking at that object, right? Because how will I generate? Oh, I can generate this H, right? All I have to do is to compute compute the H of this index and get the number. You understand my point? Suppose this is an index, right? It is index from 1 to n. Where do these functions are? Hi is from 1 to n to plus 1 minus 1, right? This is a function. Now, how do we compute this function? Hi of some a is nothing but you look at that polynomial and you just evaluate it. And to evaluate this polynomial, all you need is this number a and all these coefficients of that polynomial, and then you are able to do that. Right? So all the coefficients I have the index, so I can compute this number. And once I compute this number, I just look at what is this Eij. Like this just tells me that, oh, only that place you should be adding delta j. So basically it means that this particular column everybody should be adding delta j. So I can compute each of these entries, and for each of these entry I multiply with delta j and add it to the corresponding zi, and I'm done. Right? So this operation can also be done in a small space, and it is important that we do all these things in small space. Okay? So this is a small sketch of these things, and if you do all this variance computation and everything, it will tell you that this will succeed with good probability, like because you have taken so many copies and all these copies are independent. So which is same as running this algorithm independently or parallelly. Okay, so I will not get into that details at this point of time, but okay, so I will move to doing something else now, and we will come back and do more moment estimate when we are mature. I mean, we are still not mature to handle p-stable distributions. Okay, so let's do slightly more easy thing, which I was anyway planning to do. So you understood what linear sketch is, and AMS F2 estimate is a linear sketch. Okay, and now, and so three things to remember: what is linear sketch, what is turnstile model, and things like that. Okay, let me see how much you know, how much we all know an algorithm to compute the first algorithm that we learn in our first basic algorithm course, let's say. So I'm going to do something called, which I'm sure you get in your assignments. Should I rub this? Because we're going to move to what is called frequent items. Okay, so the next topic which we'll cover is what is called frequent items. So from now onwards, when next time I do a sketch, I will do all the analysis, because the same analysis will also work here. So I did not bother. So what is frequent item problem? So what is Fk when k is infinity? Right? This is basically maximum frequency. Okay? So it's computing maximum frequency, and if we just assume that we have numbers from 1 to n and I want to compute the maximum frequency. This is very brittle and it's very hard to approximate, and you can prove amazing lower bounds for this, which we will do. So we do something else. Okay, so for example, and this also leads to what is called heavy hitter problem. So what is heavy hitter problem? So what is heavy hitter problem? So find all items I. So this is what is our topic will be. Find all items I such that frequency is more than m by k for some fixed k. Right? So these are the items, like you fix k, so these are the, and m is the size of your stream, right? So you want to output all those elements which occurs very frequently in your stream. Okay? And for k equal to 2, what is this? This is basically what is called majority element. So now suppose you are given a list or an array, not list, given an array list of m elements or m integers. Okay, is there an element, that occurs more than m by 2 times in A? A. And in the streaming we will ask, is there an I such that n by 2. Okay. So do you know an algorithm for this? Like static algorithm. I'm not asking streaming with streaming. So yeah. N square algorithm itself. What will you do? What?
Take element, check the frequency, go across the
Excellent. So how much time does this algorithm takes? N square time. Can we do better? You understand the question, right? So you're given an array of m numbers and you want to count, you want to check whether there is a number which occurs at least half the times. And he just proposed that you take each element, just check how many times it occurs. If any of them occurs more than m by 2 times, you output.
You can sort.
Or you can sort, okay, so he, and then?
Go from the start to the end, and like for every number you can keep a counter and finish once that number is not in your list.
No. So what you were saying?
You sort your array.
I sorted my array.
You look at your first number. Put a frequency is equal to 1. If the next number is different, then you again start your frequency with 0. Like you can keep a count, like what is the maximum frequency of any element.
Okay.
So that's n log n.
Okay, so that will take m log m. So yeah, this is fine. Can you do better?
We can just maintain a n size array and go through.
No, these are integers. I wrote on purpose. They are not numbers between 1 to n, so that you can do your index business. I thought and then I changed. We are not talking about streaming. I'm just talking about array. It's a static. Forget about streaming. I'm just talking a static version.
So when a new number comes, you need to figure out whether it has already. So there is no upper bound on this n.
What? Yeah, there is no upper bound on n. Absolutely no upper bound on the range. Even I'll give you a streaming algorithm with no upper bound on the range. Otherwise, what's the fun?
So far we have an m log n.
M log m algorithm.
Do it in linear time.
Okay, let me teach you a streaming algorithm. It will not run in linear time, so it's fine. I don't give away the answer. Okay. No, it will run in linear time. So but okay, fine. But it's a very cool algorithm. So I actually did not understand it till today morning, but it is a very, very cool algorithm. By the way, first. So now I want to do streaming algorithm for majority. And it's only insertion, no deletion business, because then it makes life very, very hard. Okay. So just like numbers are coming and you want to do majority, and like just exactly like this, like array setting, but you don't know, like one numbers are coming and you have to find majority. But unfortunately, if you cannot do it in less than omega n space in one pass. Omega n m whatever, nothing. Okay, so you need more than one pass. Okay, but two pass is enough. Okay.
So just to finish up the static algorithm, one thing you can do in linear time is to find the median. Okay, we can find the median in linear time, and
Then what? I mean, Venkatesh has given away the algorithm, but no, no, no. I'm saying that now, if you are not able to figure out, then that's yeah, exactly. So this is what I'm going to do now. You will see. Yeah, it's way more cuter. Like this is like. I mean, before I go to heavy hitters with K, I mean, then it becomes very, very difficult. I thought at least make them play. I mean, I actually tried last night, and then I had some intuition. Then later, I mean, it's like really. Okay, and I'm on purpose not explaining. I'm writing it in code. Okay, so while stream is not empty, I'm going to do the something very nice. So this S is supposed to be my perspective majority. This is what you should be. And C is how many times this guy has occurred. So this is the two things to keep in head. S is our perspective majority and how many times this S has occurred. Okay. If the current element Ej equal to S, then what should I do? If S is my perspective majority and my current element, okay, stream is this, what should I do then? I should increase its frequency C to C plus 1 because S is storing, okay. Else if C equal to 0, so C is 0, what will I do? C equal to 1 and S equal to Ej. You are my current like prospective element. Else, so see, I mean, so you are not, so whatever my current perspective majority, which I'm thinking it is, you are not my majority because you are not equal to that. But see, like, but I have some majority in my head perspective. So else I will do C minus 1. Okay, end while. That's it. I'm done. For now, suppose I'm telling you this algorithm is correct if there exists. So claim, okay? If there exists a majority and there is no randomization, nothing, it's a completely deterministic algorithm. Claim, if there exists a majority, then S is the one. Okay. Furthermore, I will not say this because if I say this, it's easy to view. Okay. Why? I mean, I can tell you the answer, but that's not fun. I mean, this is not something which you cannot do it yourself. Okay. But how much space will this take? Forget about, suppose this algorithm is correct. So suppose, so it could give you a wrong answer. How can it give you a wrong answer? If it is a majority, look, it gives you an S. So if you believe my claim, if there exists a majority, then S is a majority. But if this is not a majority, I will still output you some number S. So you still need to verify this is majority. It's like median, right? So I gave you a number which is median in some sense, if you notice, but that doesn't matter. So I gave you this, but now you have to figure out it is indeed m by 2. So I will do a second pass of this algorithm and check how many times this appears, and I'm done. So it is like the same like median. I first find median and then check whether median is that corresponding. So if I guarantee you that whatever S I output to you If there will be a frequent, if there is an element which is majority, then S is that majority. Given that claim, you can go over one more pass and verify yourself that this is indeed the majority. So all it boils down to proving this particular claim. And how much space does this algorithm take? It stores two things, C and S. So I mean, if so, first pass of this algorithm will take whatever you get an upper bound on n, so some log n bits, log of whatever the largest number it is going to come, because that is what you might have to store, and at most log m, because where m is the size of the stream. So it's like order log m bit algorithm, right? So two things to care. Two pass. Firstly, this is a two pass algorithm. And secondly, it will take order log m log n bits, where n is an upper bound on the max number that is in stream. What is this algorithm actually doing? If you think for a minute, every time it does two operations, right? Either a counter is increased or counter is not increased. Twice? That doesn't matter. That is, I mean, yes, that's a good point, but that is not the reason why this algorithm is correct. What? Why not? What are you talking about? Twice, C will never be decreased to 0. What makes you think that way? Just think about it, no? It will. Think more globally. Okay, so look at the majority element I. I is my majority element, which means how many times it appears? At least m by 2. Suppose it appears m by 2 plus x times, where x is greater. Now each time, every operation does two things. Either it increases the counter or it decreases the counter. Every element, when in the stream, it does either increases the counter or decreases the counter. Okay. So whatever may be the counter, because I have m by 2 plus x, whatever may be the effect of other elements is to the counter, my number may be like whichever sequence it appears, right? It is going to decrease, but at some point of time, it will go into this because it occurs more than this. And in fact, what you can furthermore, you can show that C is at least m by 2 minus its frequency, or f minus, or other way around, okay. So the argument is very simple, right? Every element, okay, has the following bearing on my counter. Either I increase my counter by +1 or I decrease my counter by +1. Now look at an element which occurs m by 2 plus x, right? When does it have an effect of decrement? Because someone else is already staying. So it means some other number is staying, right? So, but how many times that number is going to occur? M by 2 minus x. So that is the time, number of time this guy will go and decrement this counter. But every time else, this is the number which is going to increment the counter. So this is the number which is going to survive inside my S, nothing else. This also will find you majority. sorry, it will also find you the median if you define this way, because that is the number who is going to be left. So this is another way of doing median if there's a majority. Right? And the count will be at the end, its frequency minus m by 2. At least this much will be the count of this C guy. Because as I told you, right, every number, and count is never less than 0, right? It's always more than 0. Right? So I can come back to 0 every time some other number pushes it up, majority goes down, 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 it comes to 0, maybe some other number pops it up, down, 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 but at some point of time, this majority number is going to pop it up, right? So that's an argument, okay? So next time, we will take up this basic algorithm and then design an algorithm for heavy hitters, okay, in this, but heavy hitters like, so we will still give you a deterministic algorithm, but we can achieve much, much better space bounds if we allow randomized algorithms, and we'll see some of those next week. So that is what is called count, min, sketch, and blah, 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 which is the agenda item for the next week. Okay, good. Okay.